First, I would like to introduce ourselves. My name is Syed Amir Hamza. And yeah, thank you for calling me doctor, but I'm not there yet. So I'm right now I'm working at the Hochschule Heilbronn under the institution for intelligent cyber physical systems as a research assistant over there under the supervision of Professor Dr. Alexander Yesse. So he's the institutional director for ICPS at the Hochschule Heilbronn. And I'm from Bangladesh. So my research interest always surrounded to the computer vision and its related fields. So today I'm here to talk about our research on the lung tuberculosis. So before going to that, I would like to introduce a bit about tuberculosis. So basically, as the part I'm from, it's from the Southern Asia part. So there, the case for lung tuberculosis are a bit higher. And due to the lack of the service providers, we are unable to give the services for the early diagnostics, or also there are, due to the number of patients are higher and the service providers are not that much efficient in some places. So it's hard to provide the services on time, or yeah, the queue is higher, the time is also very high. So due to that, some people are not getting that proper diagnostic systems. So while my supervisor was in talk with a doctor from there, from that time, we had this idea that how we can improve the diagnostic systems by using, as we have AI's evolution now, so we can use those to make the time at least a bit faster. So the plan was to build an algorithm first to detect the tuberculosis without any issues with very high accuracy, to help the doctors to check the report a bit earlier, so that the service providers can have the idea about the patient instantly. So let's talk about a bit tuberculosis. So it remains one of the top infectious killers globally, affecting millions each year, as we know. Despite being a curable disease, its diagnosis poses significant challenges on that part. So currently, chest X-rays are pivotal in TB diagnosis, but they require expert inter-participation and can often miss subtle signs, especially in early stages of the disease. So as we know, medical images contains a lot of information inside it. So the traditional methods that we are using to detect this is in CNN, and quite bit we know about this, the convolutional neural network. It's already proved itself in this sector, but the problem over there is that it's not that much flexible in terms to get the global data. So in an image, we have this local representational data and the global data, which gives the computer about co- co- computer about the understanding of the images. So while working with this kind of images, so the algorithm first understand about the connection in between this. So if it has the global and local data both, then it can understand it very precisely in this case. So Basically, this begs the question that can we enhance the accuracy and efficiency in TB diagnosis? So, yeah, let's dive into how our research contributes to this. So, in this study, the architecture was adapted for lung tuberculosis detection is from chest X-ray images by incorporating a hierarchical feature representation and a shifted window mechanism. So basically, we have while we were talking for this solution, that time Google introduced the paper named VIT Vision Transformer. So that was a different approach than the traditional convolutional neural network. That what actually catches my mind. And the technology behind this was very fascinating. Right after that, there was a new paper called Swin Transformer, which on the top of that, it uses the hierarchical view, and also it uses the shifted window mechanism to make it more efficient in terms of learning and detecting. So till that time, there was very few cases or very rare that someone used this technology specifically in the field of detecting this tuberculosis. So that's how I had this plan, and then we talked with our supervisor, and we try to put some effort on this. So let's talk about the architecture that we have used here. So the Swine Transformer is a type of artificial intelligence model used primarily for processing and understanding the images. So it's basically originally developed for the neural language process, like right now we have behind the chat GPT there. So basically, when it's entered the Swine Transformers, it's an advanced model that um, revolutionizes how we analyze the images. So it basically bridges the gap between local detail recognition and global contextual understanding. So in TB, where every detail can be a clue, so this technologies has the capability to scrutinize images at multiple scales in invaluable. Um, how do the Swine Transformers stand apart from convolutional networks, the CNNs? So while CNNs excel in detecting local patterns, but Swine Transformer bring an added layer of context. So crucial for comprehensive image analysis in medical settings. I think let's dive into the working of the Swine Transformer. So its unique shifted window mechanism, basically it's a game changer in capturing details in the from the chest X-ray images. And this mechanisms has the ability to analyze images at different scales, in particularly beneficial for identifying early signs of TB, which can be easily missed from the normal eyes, or yeah, from other type of approaches, could be. So in our study, we applied the Swine Transformer to a dataset of chest X-ray. So this included the images with varying stages of TB, but for the time being, only on this case study, we have only focused on the positive and the negative case of tuberculosis. But yeah, to make you understand, first, I would like to tell that why we have chosen this architecture and the actual feature that I have talked about, the hierarchical feature and the shifted window mechanism. So actually here, a brief about the hierarchical feature. So it's just like the layers of the photo. So what does inside the Swin transformer when it analyzes a photo? So first, let me introduce it in simple terms. So it's like you can call a doctor. So when a doctor see a patient's report, it sees directly the report first at one look to understand maybe which part of the report is from. So it will look on the image directly at once. Then it will divide the images into different patches where it will look separately on those different patches. So here is this hierarchical feature came where at the higher levels, these lines and edges from shapes and objects, and at the lowest level, you might recognize the patterns, the lines, and the edges. So it divides in different layers, and then it gets the idea about the images on every part. And here the global representational works in a way. So when it divides the images in different layers, it gets the idea about the images, and then it can relate with the local representation and also with the global, which mean the lower levels part. So that's how it relates the images from one part to another part. Then there is this shifted window mechanism, which makes it a bit more efficient than the VIT. So here, the Swin transformer, where the image is first divided into small windows for focused processing. So it basically focus on each and every part of the images by dividing this. Then these windows are slightly shifted in the next layer, allowing the model to capture overlapping areas and integrate border image context. So then it enhancing its ability to analyze the images in both, like as I talked about, globally and locally. So that's how basically it gets the idea about the images. So here for this, we have used the dataset, and this is actually the dataset is from the National Institute of Health. It's an American organization. So the dataset, I wouldn't say it's not that huge dataset. We can call it in terms of the case. It's quite bit small data set to work with. So we distributed the tuberculosis positive, which is 304,098, and the negative images were 1,557. And then we split it into 64% for training purpose, and for validation 16%, and for texting we kept 20%. And then for the pre-processing training and evaluation, I have showed a bit here. So we resize the image to 512 into 512 pixels. Then we've done some horizontal flips for augmentation, normalization. And for the training purpose, we have completed total 50 epochs with the batch size of 8. And we have used the Adam optimizer for the loss function, we have used the cross entropy loss. And to evaluate the this research, we have used the accuracy and the F1 score, also the precision and recall here. So I would like to show you about our results. So this is we found it first. So the positive result for in precision is 0.90, and the recall is 0.9099, and the F1 score is 0.9053, whereas the negative scores a bit less, I think it's due to the data we have. So yeah, it's not that extensive data that we have. So that's how our negative results a bit less. But I believe if we train it with more, then we'll be able to get very good results later on. So here is the overall view while training. So as you can see, while training, it was yeah, it was 0.88 for the training and validation accuracy in the positive class. But for the negative class, the score was a bit lower, 0.799, as I showed earlier. So it's due to the class, of course, due to the size of the data, of course. And then here is the loss values, which explains in our case, like the training loss is 0.252. So it indicates the model's effectiveness during the training. So this value is good when it comes as less as possible. And then we have this validation loss, which is 0.292, reflects the model's performance on unseen data. And yeah, the overall insight is balance. So the closed values suggest a balanced model without signs of overfitting or underfitting. So the future work in this part, um, yeah, we can improve our model accuracy. So here we might add some more data to check our model's accuracy. And then we can also maybe do some data augmentation and data generating to enrich our data set. And also we can do some hyperparameter tuning to check in different tuning how the model works with the different setups. We can also maybe change the function of a loss function to analyze the model. And the main part, I believe, after if it gives us very good result later on, then we'll be able to work with it with the real world applications and datas. I mean, like in different kind of data, like not just the tuberculosis, but there are also other diseases which I believe would be very nice to know the potentiality of this model, and to make the to understand the model's decision, to make it very transparent and clear to the people, we can also use the explainability AI and interpretability AI in terms of optimize this for to use it like on a very lower configured computers. We can check the performance optimization later on, and we can use it with the cross disciplinary applications. At the meantime, we can check it for long-term monitoring, and then we can maintain the errors and all. So to conclude, the application of Swin transformers in TB diagnosis re represents a significant advancement in the medical imaging. It's a step towards more accurate, efficient, and reliable diagnostics. Um, I believe our journey doesn't end here. This research paves the way for a new era in medical imaging and patients care, I believe. Yeah. So yeah, thank you for all of your attention. If there's any question, please feel free to ask.